Today I'm going to talk about generative AI, architecture, and entropy. There are many different types of generative AI architectures, but today I'm going to introduce commonly used architecture. Depending on your goal and your applications and companies, detailed architectures are slightly different depending on each cases. But today, I'm going to give you overall picture of generative AI architecture. And at the end, in addition to the architecture, a more important design element is what's gonna be the loss function. And in the previous classes, I was talking about many different loss functions, such as mean square error, entropy, cross entropy, and KL divergences. Those four different loss functions are commonly used in generative AI. And at the end of this class today, I'm going to explain how we're gonna use those loss functions to train generative AI architectures. Usually, not 100%, but usually generative AI architecture has encoder-decoder structure. In these days, the most popular generative AI architecture is called as transformer model. Transformer model is commonly used for GPT-3 and 4. The other types of generative AI is being called as diffusion model. Probably at the end of this class, we will freely talk about the basics about these two generative AI models. I would strongly encourage your term project to use either generative model or diffusion model to solve your engineering problem. That is what I would expect from your term project. Transformer model. We're gonna use diffusion model. These models, generative AI model, may be used for your term project as a tool to design your circuit, antenna, or packages. When you are designing those electronic circuits using this generative AI, you may need to estimate the output. For example, if you design your circuit, you may have to estimate gain of your circuit. In those cases, DNN model can be combined together with this generative AI. At the end of your design, sometimes you want to optimize your circuit. Then you can use reinforcement learning. So in this class as a term project, you may combine this kind of generative model with DNN and reinforcement learning to complete your design and optimization. Right now, you may feel like, how can you do that in this just 3-month classes? But believe in me, you can do that. So after the class, I hope you can freely talk about generative AI with other students at KAIST who is majoring on AI. Probably you can take better idea than them. For the case of generative AI like transformer model that is being used in GPT and diffusion model, as I know that there is a generative AI called as a DALL-E. You can access this DALL-E through the OpenAI website. I think DALL-E is based on the diffusion model. So you can take good idea about that. This kind of transformer model and diffusion model has this AI architecture. It has encoder and decoder. You can put as an input to the encoder. X could be either text or image or sound. Any types of digital file could be used as an input. For the case of DALL-E, you use text input and output is gonna be an image. In other cases, you can put image into this generative AI and output could be a text. Or you can put into a text as an input and output could be a music. So input output may have different forms, but as I know up to now, 99% of generative AI has a encoder and decoder architecture. Output is gonna be either itself or different vector. Sometimes during the training process of this generative AI, you put in X vector. Sometimes you reconstruct output so that your output is same as input. Sometimes your output is compared to a reference vector. When we are comparing this output, we can use loss function. And there are many different types of loss function. One of them is mean square error. The second type is entropy. Third one is KL divergence. In most cases of generative AI, we are using this loss function. We have forward propagation and backward propagation. If we have some differences between output and target vector, sometimes we can use mean square error or entropy difference. Then we have to update this decoder and encoder network. Encoder is a form of deep neural network, and decoder may be another deep neural network. You have to update parameters of deep neural network of decoder and encoder during the backpropagation process. And you remember that this decoder has multi-layer structures. So in order to update all those parameters, we have to develop chain rules. And in the previous classes, I was giving you brief lectures on chain rules of being used during the backpropagation. In the middle, we have latent vector that is called G. Let's assume that input vector is a text. I'm a student at KAIST. Output vector is text. Then you are an outstanding student, like Hyuna and Jungmin. So this generative AI have so many experiences to work with the KAIST student, and they know most of them are probability is that you are very good students. Today, I feel like that because all of you are attending these classes. This is my brain is a kind of generative AI. I have so many experiences. Just looking at your eyes, I can feel that you are good students. But surprisingly, this deep neural network does not translate input vector to output vector directly. They decode the input to a latent vector. And latent vector is interpreted by decoder vector to generate the output. One day I was wondering, why do we need latent vector space? Here, input vector is a language of human. Output vector is language of human. I think this G vector is language of God. This is a translator between human to God, God to human. This is comic interpretations, but that's what I believe right now. You go to church and you are listening the pastor's speech, and he is an interpreter of God. Bible is an interpreter of God. Actually, I'm not Christian. So this is a Bible. We have to go to church that is called as encoder. We have to open our ears, and somebody has to interpret the Bible, depending on who is. Sometimes you are a good Christian, or sometimes you are a dangerous Christian. So this is by kind of Bible. I think 99% of the generative AI architecture has this kind of form. Why do we have a G space? I think there are three reasons for that. Number one is simplified step. Your vector has huge number of size, millions multiplied by millions matrix, and billions of data. In order to do the calculations using the computer to convert from input to the output, you may need infinite number of computers. But by compressing your input to a G space vector that is very small size n-dimensional vector, then we can easily manipulate in this domain. If you describe a tiger, we may need a one page of sentences. He has 2 ears, color of black and the yellow, and he can eat meat, something like that. But in G space, single vector can represent a tiger. More meaning is contained, but mathematically, it is very simple vector space. So if you wanna design a new image file who resembles tiger and cat, if we describe the new animals, we have to write a long pages. But here, we just add 2 vectors, tiger vector and lion vector. And by then, by using the decoder is actually interpreter, we can generate images or another simplified texts. I know that you are sometimes using the GPT file to check your English grammar or when you are writing a report. Basically, Transformer has this kind of architecture. Second one is symbolic representation. So the reason is third advantage to use the G-space vector is easier calculation. Another interesting observation I have so far in generative AI is in G space, it is not discrete. It's more likely a probability distribution. Another observation I saw in generative AI architecture is that G vector is not a discrete binary vector space. It actually has certain probabilities. So in G vector, actually mean point and variance and Gaussian distribution is assumed. It is almost impossible to define a character of teaching assistant Joungho. He's a nice guy, but sometimes rarely he's not a good guy. Sometimes he is angry. So our character has certain probabilities. You have black hair, but sometimes I saw that her hair color is changing because she went to the beauty shops over the weekend. So depending on your mother and father and DNA and environment, and there are certain distribution of colors or eyes and something like that. So this G vector is actually Gaussian distribution. Later on, we will come back to that again. So in the G vector, actually G represent mean point and variances. And sometimes you may have tiger character and lion's character, and sometimes you have mixture of them. So if you are sending a text message to say that please draw an image who has 50% lion and 50% of character, then you pick up a G vector space who has overlap. And that you have that vector that by applying decoder, you can generate the images. I think these are on October and November, we're gonna come back to this architecture again and again and again. When I was talking about transform model, diffusion models, probably in this class, I'm gonna introduce maybe 5 or 6 different generative AI architectures, and most of them have this kind of concept and architecture. So during the training process, we have to define loss function. How much our output of generative AI is close to your reference text or images. Most commonly used loss function is entropy or KL divergence. You remember that entropy is the amount of information to describe your output. Some of your output just need 1 bit data, then information is just 1 bit. Sometimes your output may have many different distributions, and then entropy is very, very high. So we usually use entropy function to train this generative AI. A good output means you need less digital information to describe your output. For example, you threw your coin and it has the face up or face down. So 1 bit is a good amount of information to describe that output. But if you are use the cube, then you have 6 different faces. So probability of 1, 2, 3 is 1 by 6. Then entropy is very high. So uniform distribution is a kind of high entropy, and discrete distribution has low entropy. So you are training this generative AI to minimize the entropy. I don't know why God likes low entropy. My heart, I have two different entropy. I have a brain who has low entropy, a high entropy, low entropy, low temperature. My brain has low entropy machine. I wanna make it clear, or I wanna make it efficient. I have heart. That system is high entropy system. When I am writing, when I am watching students' presentation, I'm using more low entropy system, whether he has a mistake or his presentation is not clear. But when I have dinner or drink with my students, I'm on more like a high entropy system. I have two different systems. At home, I'm trying to be a high entropy system. At school, I want to be a low entropy system. Joungho, who is you? Your system is low entropy system or high entropy system? Oh, okay, good. But 50%, okay? Work and life balance is needed. If you like too much, then BTS might be good for high entropy. So, but in generative AI system, when they are training the generative AI system, they are put more emphasis on low entropy system. Low entropy system means more likely clear discrimination, and high entropy system is I don't know who is good or who is bad, or I'm happy or not. It's unclear. So when you are training the generative AI, we used loss function that is representing the entropy. In some case, we are using KL divergence. KL divergence means the difference between reference entropy and your entropy. If your reference entropy and your entropy is very similar to each other, then it's a good training. In those cases, we are using KL divergence. If your output of your generative AI has low entropy, means that you may need less computing power and less memory space. It means more efficient and fast. But anyway, probably if you are designing the generative AI model or to use that, you can choose one of the loss function as mean square error. That means your output and reference will be compared numerically. Second entropy is you make sum of all the element of entropy output, and you apply the back propagation to minimize the entropy. Third one is cross entropy. Cross entropy means the average entropy. This is the total entropy. This is average entropy, and weight of this entropy is applied by your reference output. This could be a mirror, and this could be myself. Log 2 yi is the output of your generative AI. This is some amount of information about myself, but how can I know that? By looking at the mirror image of yourself that is multiplied by yi dash. If your mirror has red color, you will see only red information of yourself. So that red, yellow, blue, that kind of window is controlled by reference. That is being called as cross entropy. Once again, I would like to remind you that today I'm going to talk about generative AI architecture and loss function. And last one is being called as KL divergence. The last one that is also commonly used in generative AI, such as transformer model and diffusion model, the loss function is being called as KL divergence. The last term is cross entropy of reference. This is cross entropy of output. So the last KLD is comparing the cross average information of output and average information of reference. If those are very close to each other, then means you have very good training process. It may not be easy for you to take good idea about this architecture and loss function, but I'm sure that as our lecture goes on in a month, you will take a better and better idea on this. One of the I think about 10 years ago, variational autoencoder was quite popular generative AI architecture. And I'm going to shortly introduce that one. Variational autoencoder. In the first week of October, I'm going to spend 2 lectures to describe very details about autoencoder, variational autoencoder. Then I'm going to talk about GAN and diffusion models and so on, and transformer model as well. It has this kind of architecture. it has encoder. Encoder has input vector represented by vector x, and output of this encoder will be latent vector g. Of course, the size of g vector is much smaller than x vector. And of course, g vector is not discrete numbers. It may have certain distributions, usually Gaussian distribution. And q represent encoder, and pi represent the model parameters. In the previous classes, model parameters of deep neural network was written as W. Sometimes I was representing the model parameter by theta, but here in the variational autoencoder, we describe the deep neural network parameters as a pi. This G latent vector is transmitted to encoder by sampling process. We have decoder and we have output. During the training process, what we are asking variational autoencoder to do is to repeat itself. First, we train them so that by applying the encoder and decoder, it has capability of reconstruct itself from latent space at G. Let's assume that it has good training, then entropy of KL divergence, actually entropy of output and input will have almost the same numbers. That is the result of good training. Then after the training, you just use this part, decoder part for generation. You manipulate G in the G space, and then you can generate new images. That is the overall process of the training and inference. Now, at this final moment of the class, I would like to give you a mathematical description of loss function. What's gonna be a form of loss function of generative variational autoencoder? Please write it down, this loss function, and I'm going to talk about the meaning. This is architecture. And this is loss function. If I have to explain very core concept of variational autoencoder, variational autoencoder is very symbolic generative AI architecture, then I would use these two figures. One is to show the architecture, and second one is to show the loss function. If later on, sometime in the future, if you want to design a new generative AI, probably you have to start with this architecture. Now, how you gonna train them? How you after the train, how you gonna generate the new images or texts, and how you gonna define the loss function. Even though recently we have diffusion model, stable diffusion, and GAN or transformer models, I think it starts with this variational autoencoder. Let's talk about the meaning of this loss function. Theta is actually model parameters of deep neural network of decoder. Pi is a model parameters of deep neural network of encoder. This representation means that you have to train this theta and pi to minimize this entropy and KL divergence. That is the mathematical description of argument minimum. That means you have to optimize theta and pi to minimize this whole equations. Of course, when we are applying the backpropagation, we have to do the derivative gradient descent and we have to apply the chain rules. But initially, the kickoff of this backpropagation is determined by this equation. We have to train decoder. That means we have to optimize model parameter theta of encoder, then neural network, and pi of model parameters of encoder deep neural network. Of course, in the transformer model, we have to add another mechanism, attention matrix. That makes it much more complicated and time consuming. But this variational autoencoder will be a building block to talk about that. From next week, I'm going to talk about the attention and transformer model. But without a good understanding of this, you may not be able to follow that attention matrix and transformer models. Of course, without knowing all this architecture and loss functions, you can still use the transformer model in the internet, and you can design a new machine learning to achieve your engineering goals. But with this understanding, you may be much more confident. Let's talk about first term. PXI means probability distribution of output. Probability distribution of output. Let's take a look, and you may have discrete uniform distribution of X, that is case A. And another case is that you may have very distinctive distribution. This is case B. You remember that entropy of B is lower than case A. This first term is entropy of output. Under the condition of G, with a given G, decoder will generate X. X has certain probability distributions, and we may train theta so that we have minimal entropy. That is this mathematical description. Under a certain condition that G vector, latent vector, is generated by encoder. So the first sentence means that you have to train encoder and decoder so that your output entropy summation should be minimal. That is this first equation. I personally want to see performance of all the students very high. I like more high entropy systems. In some cases, in our educational system, they want to distinguish students. That is killer 문항. So one student got 100 points, the other students are 10, 10, 10, 10. Unfortunately, generative AI are pursuing some ununiform distribution. Like very good students, others very low students, and here is the uniform. So when generative AI is being trained, their output has to have lower entropy. Philosophically, that is unhappy, but for efficiency of computation and this, so generative AI wanna generate images has distinctive difference between tiger and lions. If there are some gray area of images, oh, I don't know, it's lions and tigers, they don't want to have that. But in human life, actually, we have many gray areas. But when we are training generative AI, we don't like fuzzy and foggy or gray areas. We want to have very distinctive images or text output. How do you do that mathematically? We are achieving lowest entropy. Lowest entropy is actually 0. And high entropy is like infinite number because of log nature. Log is actually this kind of minus log, minus and minus log graph is like that. This is target. This is infinite. So generative AI likes this 0 and 1. Probability 1, only one of element should be 1, and their log is equal to 0. That is their training target of this one. Second term is KL divergence. This G has certain distribution function. Usually we are assuming Gaussian. This latent space distribution is a Gaussian. Usually, I'm not going to prove it. Usually, if your distribution is Gaussian, entropy is minimal. So comparing the Gaussian function and your actual output of encoder, this is encoder, this is for encoder training. How are you going to compare Gaussian distribution as your encoder output? We are comparing the two different entropy. And then if they are very close to each other, then we have very good training. So during the training, we are trying to generate encoder, train the encoder so that G vector is more likely Gaussian distribution. How are you going to achieve that mathematically? We compare the Gaussian entropy and your actual entropy. Until you have very good Gaussian output, you're gonna have, you keep training. So on Wednesday, we're gonna come back again and I will repeat again. And I'm going to use this equation with some examples. Right now, it is more likely mathematical description and explanation. And on Wednesday, I'm going to use some numerical numbers to talk about entropy and KL divergence. Thank you for your attention. But what I'm very sure is that this 1 hour lecture today is the very, very core part of the generative AI. Thank you for showing us today.